we're going to look at the chain rule. So we use the chain rule when we have a composition of two functions. This is, of the derivative rules that we talk about, this is the one that tends to get the most confused and the most missed as like, ooh, that was a chain rule problem. I just missed seeing there was a chain rule here. So you guys remember composition from like your Algebra 2 class. Probably even did it last year in pre-calculus, right? So it's where you have one function like inside of another. So what the chain rule says is if I'm taking the derivative of f of g of x, that derivative is going to be f prime of g of x times g prime of x. Now, I think that's a gross notation. This is the way that I think about it. When you have a composition, you have an inside function and an outside function, right? It's the derivative of the outside times the derivative of the inside. That's, I think, the easiest way to conceptualize what we're doing with the chain rule. So it's like the derivative of the outside times the derivative of the inside. Now, oftentimes, you'll have more than one option of like what you want to call the inside and outer function, the inner and outer functions for your composition. Sometimes not. So acknowledge that depending on the problem, we may see a situation where like there's more than one way to kind of skin that cat, but we'll come to that when we get there. So let's look at this first example. We have the function square root of x squared plus 1. Do you recognize that as a composition of two functions? What would the outer function for the square root of x squared plus 1 be? Square root of x. That's great. And the inner function would be x squared plus 1. Everybody can see that. I'm going to write it out. So far, so good. So if we do the chain rule, if I think about the derivative of the outside, I'm going to think about square root of x as x to the 1/2. To do the derivative of x to the 1/2 is just a power rule derivative, right? 1/2 x to the negative 1/2. But it's not really x. It's the f prime of g of x, right? So I just take the derivative with the outside. The inside stays the same. And then I have times the derivative of the inside, which is 2x. Does everybody see that? I think when we were doing that worksheet, we had something like, x to the 7th to the 5th or something. We took the derivative of it. And I think Alex said, oh, this is just the chain rule, right? Well, or just the power rule. And it's like, well, not exactly, right? Because there's actually a chain rule to do that. I'd have to take the derivative of the inside. We just got lucky that time and the derivative of the inside was 1, so it didn't end up mattering. So that's, just want to tie it back because we're very close to like stumbling into that. Okay, so now we could simplify what we've written here, right? For Mr. Kulik, if this is a free response question, do I need to simplify what I've written here? No. Once the calculus is done, you can stop. Looking at tests, there's a lot of time spent like simplifying and doing algebra. Your calculus is done, you can stop. Now, if this is a multiple choice question, this would not be one of the answers in the multiple choice question. almost assuredly they would write it as that, which again, if it's a multiple choice, you have to simplify down to what the choices look like. But if it's a free response question, don't waste time simplifying. Once the calculus is done, stop. You don't need to FOIL things out. You don't need to make common denominators. You don't need to reduce fractions. You don't need to combine like terms. On the AP exam, in a free response section, when the calculus is done, you are done. Okay? Particularly because if you make an algebra mistake, you then lose points. So if you finish the calculus correctly and then make an algebra mistake to your final answer, I think you lose, the doing it correctly point. Everybody okay? Okay. Let's continue here, do another example. Here we have sine of x squared, and then after that we're going to do sine squared x. So for sine of x squared, what is our outer? Sine x. And what's our inner? X squared, right? Okay. So the derivative of our outer, what's the derivative of sine? Cosine. And then still have the inner inside. And then times the derivative of the outer, which is 2x. And there you could stop. If you wanted to clean that up, there's not really much cleanup to do, right? If we look at part B, what's the outer function for part B? Not sine squared. It's not at sine x. So keep in mind, what does sine squared really mean? It means sine x squared, right? So the outer function is x squared. Yeah. And the inner function is sine x. You guys see that? So again, like the key here, as oftentimes in calculus, is can I look at this and manipulate this algebraically into something where, oh, if it looks like that, now I know exactly what to do with it, right? The saying for calculus is it's the calculus part is the easy part. It's the algebra parts that are the hard part. Like remembering, how can I rearrange this to make it easy? Or what can I do to like simplify this down to make the calculus easy? But it's the algebra that's often the killer here. Okay, so if I do the derivative of the outside, that is going to be, the derivative of x squared is 2x, but we plug in our g, so it's 2 sine x. And the derivative of the inside is cosine. Now that answer is fine the way it's written. Does anybody recognize that as a trig identity though? 2 sine x cos x. It's the double angle formula for sine. Do I expect you to do that? No. But if you looked at like an answer key, it wouldn't surprise me if that's what they wrote it as. I'd be surprised on a multiple choice question if they did that. I don't think that would be an expectation, but everybody's okay? So far, so good? Okay. So this is a essentially a formula here that's just saying, what if I have the power rule combined with the chain rule? So u is like my inner function. So this is saying we'll just do the power rule and then multiply it by the derivative of u, where u is the inner piece. Is this necessary to memorize this one? No, it's just a specific version of the chain rule. Like why specify it? I don't know, but that's what they did. So if we look at this guy here, this example, let's try to do it without writing anything else down. Let's just go straight to the derivative. The outer function is x to the 100. So the derivative of the outer is 100 inner function to the 99th. And then I have times the derivative of the inner, which is 3x to the second. Again, you could stop here, or if you wanted to combine some like terms, I guess you could do this. Can I distribute the 300x squared inside? Definitely not. Why not? Why can't I distribute that 300x squared inside the parenthesis? Yeah, because the exponent, you'd be breaking the order of operations. I have to do that exponent before I can multiply. Everybody's okay? Just wanting to point out some of these little like algebraic guys. All right. What about this one? How do we want to approach this? Charlie? Yeah, so we'd want to think about this as that. The advantage there is what do we get to avoid? A quotient rule, right? Which is a lovely time saver because the quotient rule takes a ton of writing to do. That's my number one that I want to avoid having to do unless I really have to do it. I don't want to do the quotient rule if I don't have to. One chain rule sounds pretty good. If I did the quotient, I'd have to do a quotient with a chain rule inside it. Yuck. I don't want to have to do that if I don't have to. Sometimes you do, and it's unavoidable. But let's not make our lives harder than it needs to be. Go slow, look for the back door. Try to make the problem as simple on the calculus side as we can by doing a little bit of algebraic manipulation. All right, so what is our derivative going to be then? Who can tell me? Great. Okay. Perfect. Lovely. Sounds so good. So far, so good. And if I wanted to simplify this further, you would not need to do that. But what I would expect this would have looked like. If it was like a multiple choice question, I would expect to see that. Oops. Yeah, got that 3 down there. Thanks. Does that feel okay? So far, so good? You guys are doing great. Let's look at 5. What do you see? You should see a chain rule and a quotient rule, right? That quotient rule is unavoidable. There's no simplifying I can do to that fraction to avoid having to do the quotient rule. Which one is coming first? The chain or the quotient? The chain comes first. Because what is the outer function? X to the 9th. What's the inner function? The fraction, right? So it won't be until we need to differentiate the fraction, the derivative of the inside, that we need to apply the quotient rule. Did you guys see that? Okay. So we're going to have the derivative of the outside, 9 inner function to the 8th times the derivative of the inside. So that's the quotient rule. Top times the derivative of the, or I'm sorry, the bottom times the derivative of the top minus top times derivative of the bottom all over bottom squared. And again, calculus is done. We could stop here. Not wrong to stop. Unlikely that this would be the multiple choice answer though, right? So the multiple choice answer I would expect, if I combine my like terms here, I have 2t plus 1 minus 2t plus 4. So I'd end up with just a 5 in the numerator. Everybody okay there? So I would expect to see 9 times 5, 45, t minus 2 to the 8th over 2t plus 1 to the 10th. Alex.
Would it be just to, if we left the question like that?
Yeah, would have been fine. Yep, would have been fine. Now, if you kept going and you made an algebra mistake in there, I probably took a half a point. But if you got to that point, it's okay. Does everybody feel okay? You see how I simplified the thing on the left to the thing on the right? Hopefully. If not, you can ask. If you need more steps, I'm happy to do them. I'm just trying to like go slow and talk through things. All right. Next example. What do we see here? You see a product rule and 2 chain rules, right? Which one has to come first? No. The product. Because the 2 functions that are being multiplied together are the ones with the chain, right? So if I go to differentiate this, the first thing I have to do is take care of the product. And then when I differentiate the 2 pieces of my product, that's when I'll get my chains. Right? So this will be, so the first function, I'll write out some steps here a little bit, times the derivative of the second. That will require a chain rule. And then the second function times the derivative of the first. And that will require a chain rule. Is everybody okay with how I saw the product had to happen first? Okay. So when I do the derivative of x cubed minus x plus 4 to the 4th, or plus 1 to the 4th, what do I get? And then for inner, well, let's just say inner. We don't have to, when we're just calling out answers. To the 3rd. Yep. 3x squared minus 1. Yes. Okay. And then we have our next chunk. And then to do the derivative of 2x plus 1 to the 5th requires another chain rule. What will that be? Two, correct. Everybody feel good? Now that answer could be done. That's simplified, or that all the calculus is done. Now, your answer on the multiple choice would not look like this. We would simplify this. So how would they simplify? How would I go about simplifying this? So I would notice that between these two terms, I have 2x plus 1's in common. And I have square root of, or I'm sorry, x cubed minus 1 plus 1's in common. Right? Everybody kind of see that? So what's the greatest common factor of my 2x plus 1's? How many 2x plus 1's? Well, between the two, 4 are in common to each, right? Do you see that? So I'm going to factor out a 2x plus 1 to the 4th. And how many x cubed minus x plus 1's are in common to both? 3. So that's where I would start. And then what are we going to have left here? In the first one, I'm going to have one more 2x plus 1. I'm going to have the 4. And then I'll have the 3x squared minus 2. And the second one, I'll have one of those x cubed minus x plus 1's. And then a 5 and a 2. And then I'll just work on foiling out and combining like terms after that. But like what I've done with that first factoring step simplifies this enormously to get the right answer, right? Like I'll end up with a factored answer. I don't have to do any additional factoring or foiling anything out, like yuckarooskies, foiling that thing out. Like I don't want any part of that. And if I did, I certainly wouldn't want to have to factor it back afterwards. No, thank you. But what we did there is super helpful. So let's see, I have 6x cubed, and then times 4 is 24x cubed. And then I'll have 2x, and then times 4 is negative 2x times 4. And I'll have 3x squared times 1, and then times 4. And then 1 times negative 1, and then times 4. And then we got these guys. That's easy because I'm just distributing a 10 through. So let's see, I have 34x cubed, and then minus 18x, plus 12x squared, and then plus 6. Yeah, Aaron?
Why is it negative?
So I did 2x times negative 1, and then times times the 4. That's where the negative 8x came in. Does that feel okay? So there's our factored answers at lunchtime here, folks. Okay. Let's all right. Continuing on, just going to do some more chain rule examples. So here we have the derivative of e to the sine x. What is my outer function for this one? E to the x, and the inner is sine x. So the derivative of the outer is e to the inner, right? And then the derivative of the inner is cosine x. So that's as good as we can do, right?
Is that coming from the projector?
It's the fan on the projector is squeaky. Yeah. Great, isn't it? All right. So here we have a new derivative rule. Super important. So this is another derivative shortcut. This is one that will need to be memorized. The derivative of a to the x is a to the x times the natural log of a. So if we wanted to prove that, what are we going to do? What do we think? What do we use to prove any of these derivative rules? Don't think we want to be graphing. So here's the idea. What if I write this as if I write it like this? Right? What is e to the ln a? That's just a, right? So we see that this is still the same thing. Everybody agree? So if I do the derivative then of a to the x, I can do that as just the derivative of e to the ln a to the x. Actually, let's do one more simplification here before I do that. So an exponent of an exponent, how do those simplify? They multiply, yeah. So let's do that. Now that looks like a chain rule problem now, right? What's the outer function going to be? E to the x, and the inner is natural log a times x, right? So the derivative of the outside is that times the derivative of the inside. What's the derivative of ln a times x? Just ln a. Remember, ln a is just a constant, right? So just like the derivative of 2x, it just looks gross, but it's easy to do. And remember, this is just a to the x. And there we go. It's exactly what we tried to prove. Okay. So think about e to the x. When you take the derivative of e to the x, does this rule still work? So we'd say the derivative of e to the x is e to the x times the natural log of e, right? What's the natural log of e? 1. So that's just e to the x again, right? So it still incorporates that derivative rule we knew already for e to the x. Still works. There's actually a chain rule going on in there that we didn't ever acknowledge. Yeah, Michael?
How is a to x the same as e at the log?
Okay. Say it again there for me.
Like the two circle part causes.
Oh, okay. So e to the natural log of a is just a, right? Exponent base e cancels out log base e. So you're just left with the exponent a, right? It's the, like we have like log base b of b to the x is just x, or b to the log base b of x is just equal to x. It's like the inverse property of logarithms. Does that ring a bell now? Okay. All right. So let's look at this next example. Okay. When you look at this, what do you see? Yeah, but how many? Yeah, I see a chain within a chain, right? So what is our outermost function? Sine x. So I'll do the derivative of the outside. And then we have the inner stuff. And then times the derivative of the inside stuffs. Everybody okay there? Now to do the derivative of cosine of tangent, what do we need to use? Another chain rule. You're like, oh, Mr. Kulik, will this happen a lot? Yes. Getting like nested derivative rules is super common. So the outermost function is now cosine. The derivative of cosine is negative sine of the inner function. And then we have times the derivative of the inner. And what's the derivative of tangent? Excellent. Everybody okay with what I did there? On this kind of problem where you have like chain rule with inside of chain rule, I think it's super helpful to make sure you're like just doing one link of the chain at a time, at least until you're like, I'm a pro and I can see it all the way to the end in my head. It's hard to do that at the start though. I really encourage you to like derive the outside times derive the inside, write the derive the inside piece down in case there's extra stuff to do there. But this is super common. Let's take a look at the last example we have here. Differentiate y equals e to the secant 3x. Yes, sir.
For the last question, where's the negative sign?
Oh, I put it out front.
Oh, okay.
I just moved it all the way to the front because I didn't want it to look like subtraction inside of the problem. Okay. If we look at e to the secant of 3x, what do we see there? Two chains, one inside of the other, right? The outermost chain is going to be e to the x and secant 3x. The innermost chain is going to be secant and 3 theta. Everybody see that?
So do you go outer?
Yes. Always for the chain rule, you're working from the outside in. Everybody's cool? That's a great question, though, Nate. Okay. So, derive the outside. It's just e to the inside. And then times the derivative of the inside. The derivative of secant is? Excellent. Secant times tangent. So secant of the inner, tangent of the inner, times the derivative of the inner. Oops. I should be writing d thetas down there, not d dx's. And the derivative of d theta is just 3, right? So I'll just write it this way. How do you guys feel? It's okay so far? This has been an all right day. I want to show you some stuff we can do on our calculator here, now that we're getting deep into some of these derivative problems where it'd be nice to be able to check our work to some extent, right? If you have your calculator with you, I invite you to take it out to follow along. I think it'll be helpful. do this one. This is a little bigger. Yeah, of course. Anytime. If you want to borrow one of my calculators, you're more than welcome to do so. All right. So let's say we're doing this last example problem. Y equals e to the secant 3 theta. And we got our answer, right? The answer that we just wrote down. What I want to do is kind of show you how we can check this with our calculator to make sure that the answer that we got is correct. Super helpful to be able to do this. So what I'm going to do is I'm going to be doing this graphically. So I'm going to start by just typing in the starting problem. Now, how do I do secant in my calculator? Excellent. 1 over cosine. And I'm not going to want that to graph, so I'm just going to unhighlight the equal sign so the calculator doesn't graph that for me. So that's just the starting problem. Everybody's okay?
How do you get it on?
So you just move your cursor onto the equal sign, press enter, and it'll unhighlight it. Next thing I'm going to do is I'm going to type in the answer that we got. So we said the final answer was 3 e to the secant 3x times tangent 3x. So I'm going to type that in. I thought it was going to be done doing that to me. Wasn't it nice having a little reprieve from that? Ugh. This is my life every day. It's like the universe hates me or something. Okay. So there's that. And I guess I probably should squeeze a times sign in here. I think it'll be fine, but no harm in doing that. Okay. Everybody so far so good? Just typed our answer in. And I do want that one to graph. What I also want to do is ask the calculator to graph the derivative of y1. Your calculator can do this. Ooh, tell me more, Mr. Kulik. This is how you do it. We're going to press the math button. And we're going to select from the very bottom the command nderive. So there, look, we're getting the ddx. So I need to fill in the x at the bottom. And we want to do that on the equation in y1. So right here inside the parenthesis, I want to type the y1. To get y1, I press vars. I go over to the yvars section, select function, and there's my y1. And then at the bottom, I want to just type in x equals x. Everybody okay with what I did here? So basically, this is just going to have it's going to have the calculator graph the derivative of y1. So what I'm going to do is I'm going to watch my calculator and see if my red graph matches my black graph. And I'm just going to do that on like a standard window. So there's my red graph. Here's my black graph. What do you think? Did we did it? Looks the same to me, right? Now you might say, oh, Mr. Kulik, looks like there's little red sections here, blah, blah. It's fine, right? Like, because this has the asymptotes in there and the calculator has only so much resolution, what you're seeing is like the calculator trying to reconcile how to graph stuff when it's too steep for it to deal with. So just getting confused, but it's fine. This is good. You guys agree? It's cool. Look, where have you been my whole life telling me this? Let's check another one. right? What if we did this the second to last one? Sine of cosine of tangent of x. Here's the beautiful part. The y1, sine, cosine of tangent of x. I'll update that. And my answer, I'll update that. So it's negative cosine of tangent of x times sine of tangent of x, and then 1 over secant squared. But my y3 doesn't need to change because all it's telling me is take the derivative in y1. So I can just stay there, man. All right, I don't want to graph the y1 though, so I'm going to unhighlight that. Just say graph. So there's my answer. There's the derivative. Whew, buddy, that looks pretty nice.
Did you square your cosine?
I did. Yeah, I did 1 over cosine squared. Go to the end. So I did it like that. What do you guys think? Is that helpful? Boy, that's a nice test checker, right? And it's quick. Calculator doesn't take a ton of time to do that. It's like almost instantaneous. Typing the stuff in is the hardest part. But that's pretty nice. So if I wanted to say just take the derivative of this thing at, say, x equals 5. So I can do that here also if I go to the main screen and I do that math n derive ddx. I'm going to make that y1 again. So vars, y vars, function y1. And I can put like a 5 here. So that's the derivative when I've plugged 5 into it. That's super nice. Your calculators aren't able to give you the answer to like just do the derivative, like give me symbolically with x's. If you had one of the fancy like CAS calculators, they can do that. If you know somebody, I think Joseph McDonald has one. That was funny, apparently. That's the only person I can think of offhand that I've seen with having one of those. What do you guys think? Today okay? Okay. I think I'm done. What do you guys? Are you guys done? Yeah, it's been